There is a place on this planet most people will never witness. Not because it is forbidden, not because we lack courage, but because the Earth itself seems determined to keep it hidden. Tonight we travel to the far north, past the storms, past the drifting ice, into a world that has remained sealed off longer than our species has existed. Beneath the Arctic glaciers lies something vast, dark and unreachable. A domain locked under frozen weight, older than the first human tool. Settle in. Let the noise outside fade. What we are about to explore has been concealed for millions of years. The North Pole is not what people imagine. It is not a mountain crowned with snow. It is not even land. It is a floating shell of sea ice, drifting above an ocean that never quite sleeps. When we picture it, we see an empty white horizon, broken only by ridges of wind-carved snow. But that is only the surface. Beneath that quiet, the real Arctic begins. Down in the dark are rivers that never meet air, lakes that have never reflected sunlight, cavities sealed off for hundreds of thousands of years. And in those isolated spaces, entire ecosystems may have evolved untouched, shaped by pressures no surface life ever experiences. We haven't studied them. More accurately, we cannot. Every attempt to reach the world beneath the glaciers is erased by the ice itself. Machines freeze, drills seize, sensors fail, and the boreholes we open close again, as if the glacier is swallowing them. The deeper we try to go, the more determined the ice becomes. And yet, this resistance only draws us closer. Because somewhere under all that frozen mass is a world that feels half Earth, half alien. A world we are desperate to understand. To grasp why it is so hard to reach, we first need to understand what it is we are trying to reach. Glaciers are not solid slabs, sitting silently in place. They are rivers of ice, flowing slowly under their own weight. The glaciers surrounding the Arctic are among the oldest on Earth. Some have been building for more than 2 million years, layer upon layer, compressed by time. Imagine snow falling year after year. It never melts. It compacts into ice, then more ice, and eventually into a frozen mass so thick it begins to move. Over millennia, that moving ice reshapes the ground beneath it, carving valleys and grinding mountains into dust. These aren't frozen ponds. They are colossal structures. In places, the ice covering Greenland and the Arctic Ocean reaches depths of more than 3 kilometers. Stack 3 Eiffel Towers on top of each other, and you still wouldn't break through. Under that unimaginable weight, the Earth changes. The pressure crushes the landscape below. It creates hidden basins and deep channels where meltwater collects. Sometimes the pressure alone generates enough heat to melt the bottom layer of ice, even when the surface sits in a deep freeze. That meltwater forms rivers and lakes sealed away beneath the glacier. These lakes aren't the ones you explore in summer. They are pitch black, oxygen poor, and locked beneath kilometers of crushing ice. Yet some may have existed undisturbed for hundreds of thousands of years. We know this because of Antarctica. There, Lake Vostok lies beneath 4 kilometers of ice. It may have been isolated for 15 million years. The Arctic almost certainly hides similar worlds, but they remain invisible to us. Radar hints at their presence. Satellites reveal tiny bulges in the ice above them. But to study them properly, we would have to reach them. And that is where the true difficulty begins. Drilling through kilometers of Arctic ice sounds simple on paper. In reality, it is one of the hardest engineering challenges humans have ever attempted. Ice is not the uniform solid material people imagine. It changes character as you descend. Near the surface, it behaves like fragile, brittle crystal. Deeper down, under crushing weight, it flows like cold, slow-moving tar. It bends, it shifts, it squeezes shut whatever path you try to carve through it. Traditional drills were never designed for this environment. They expect solid ground, not a medium that behaves like a living material. Even specialized thermal drills, built specifically for polar research, face severe limitations. As the drill sinks, the ice around it warms, melts slightly, and then freezes again in the wake of the descent. The borehole begins to close. The deeper you go, the harder it becomes to keep that channel open. If the ice seals behind you, the entire operation is lost. And reaching the bottom introduces a different threat. Contamination. Anything living beneath the ice, if it exists at all, has been sealed away for hundreds of thousands of years. Introducing a single microbe from the surface could erase an entire ecosystem before we ever discover it. So every component, every hose, every droplet of drilling fluid must be sterilized. A single oversight can invalidate years of preparation. The Arctic makes all of this worse. Unlike Antarctica, where many ice sheets rest on bedrock, the North Pole sits atop drifting sea ice. It shifts constantly, with the ocean currents below. A drilling platform might be perfectly positioned one day, then drift miles off course the next. A crack or pressure ridge can tear equipment apart without warning. Then there is the cold. Temperatures fall below -40. Winds reach hurricane force. For months at a time, the sun never rises, leaving researchers in total darkness. Every bolt, every joint, every electrical component must survive those extremes. And every mistake is amplified by them. Some people ask why we don't simply send submarines. After all, nuclear subs have navigated under the Arctic ice cap for decades. The reason is simple. Submarines operate in open water. They cannot navigate the violent, jagged underworld beneath a glacier. The underside of a glacier is unpredictable. Ice formations plunge downward in sharp ridges. Caverns open and collapse without warning. Channels twist into narrow choke points with no clear exit. It is a labyrinth in constant motion. Even the most advanced submarine would be blind there without extremely detailed maps. And those maps don't exist because we can't reach the area to create them. The problem circles back on itself. We can't map the under-ice world because we can't get there. And we can't get there because we haven't mapped it. So we turn to robotics. Autonomous underwater vehicles can slip into places too dangerous for humans. They can map terrain, collect samples, and operate in near-total darkness. But even they face severe constraints. Communication through thick ice is almost impossible. Radio signals fade instantly. Acoustic signals scatter and distort. Once a robot goes beneath the ice, it is on its own. If it gets trapped, if its sensors fail, if a collapsing channel crushes it, there is no rescue. Battery life adds another barrier. Bitter cold drains power rapidly. AUVs must return to the surface to recharge, but beneath a glacier, there is no surface to reach. Then there is pressure. Deeper channels experience hundreds of atmospheres of force. That pressure can bend steel and shatter composite materials. The ice itself grinds against the rock below, creating forces we still don't fully understand. A perfectly designed system on paper can fail instantly in practice. Every attempt to explore these depths teaches scientists the same lesson. we still underestimate what the Arctic is capable of. And the deeper we go, the more unpredictable it becomes. This is why progress has been painfully slow. Not because we lack ambition, but because the environment is more hostile, more dynamic, and more unforgiving than any place humans have tried to reach. And this is only the beginning of the challenge. The Arctic looks frozen from the outside, still eternal. But that image is a lie. A glacier never sleeps. It moves, it stretches, it flows. Not fast enough for the human eye to notice, but fast enough to reshape entire landscapes over years, decades, and centuries. Beneath the surface, nothing stays the same. The ice flows outward like a slow river, pushed by its own weight. The movement might only be meters each year, but over long stretches of time it carves valleys, collapses caverns, and rewires the hidden waterways beneath it. A lake that exists today might be gone next season. A tunnel detected by radar might vanish before the drilling equipment arrives. The Arctic underworld is a shifting labyrinth, a moving target in every sense. This constant motion complicates everything we try to do. Scientists plan missions years in advance. They identify a cavity or a suspected lake, build equipment, raise funding, and prepare to drill. But by the time they arrive, the landscape beneath the ice can be completely different. Channels seal, new ones open. Ice shifts and twists. The ground below rises or sinks under pressure. Even the thickness of the glacier changes. Snow falls, snow melts, ice compacts. Warm seasons and cold seasons layer new material on top of old. Every cycle reshapes the structure from above and below. And the closer we look, the more unpredictable it becomes. Climate change is speeding everything up. The Arctic is warming faster than almost anywhere else on Earth. Ice that was stable for centuries is thinning. Sea ice retreats earlier each year. Meltwater drains into new pathways. The entire system is being pushed out of balance. Some of these changes might help us. Thinner ice can be easier to drill. Warm seasons can expose new entry points or open melt channels that weren't navigable before. But the downsides hit harder. Ice shelves fracture without warning. Crevasses form in areas once considered safe. A stable platform for drilling can break apart in a single storm. Even the subglacial environment reacts to warming above. Temperatures shift beneath the ice. Pressure changes. Channels reroute. Lakes drain or swell. Ecosystems, if they exist, may become disrupted or washed into the ocean before we ever reach them. Every variable changes another. It's a chain reaction, unfolding in the dark. And yet, despite all this, scientists push forward. Not because the challenges are small, but because the stakes are enormous. Hidden beneath the Arctic glaciers might be clues to how life survives on the edge of existence. Microbes adapted to darkness, pressure, and extreme scarcity. Studying them could reveal how life persists in places we once believed impossible. The sediments under the ice hold ancient stories. Layer upon layer of frozen history, untouched for hundreds of thousands of years. They contain evidence of past climates, ancient atmospheres, and long cycles that shaped the Earth. Unlocking those stories could help us predict what's coming. And the physical processes beneath the ice matter too. They influence sea levels. They influence ocean currents. They influence the future of the Arctic itself. But to reach any of it, we face the same old problem. The ice will not stay still long enough for us to catch it. And that brings us to the next piece of the puzzle. Because the difficulty isn't only the ice that moves. It's also the tools we use to reach what lies beneath. and the ideas scientists are trying to build for the challenge ahead. There's a point in every exploration story where imagination steps in. The Arctic forces that moment earlier than most places on Earth. Because once you understand how unforgiving the ice is, you also understand something else. If we ever reach the world beneath it, it won't be by repeating old ideas. It will be by inventing completely new ones. Some of those ideas already exist. Some are only rough sketches on whiteboards in laboratories. But together, they represent the first real attempts to pierce a barrier that has stopped us for decades. One of the most promising concepts is the cryobot, a torpedo-shaped probe designed to melt its way downward, slowly carving a path through solid ice. The heat would come from a compact power source. In some designs, that source is nuclear. In others, it's an advanced thermal system capable of producing steady, controlled warmth for months at a time. As a cryobot descends, it refreezes the tunnel behind it. That's not a flaw. It's a seal, a natural barrier that prevents contamination from traveling downward. If the probe reaches a subglacial lake, it could deploy a second vehicle, one built for water instead of ice. A small, autonomous swimmer that could collect samples in complete darkness. On paper, the system works. In reality, it faces challenges that are anything but simple. A cryobot must endure crushing pressure, unpredictable layers, and zones of ice that behave more like moving tar than frozen water. Once it's below a certain depth, there's no way to retrieve it if something goes wrong. Communication becomes one way, and power must last for months or even years. Another idea takes a completely different approach. Laser drilling. Not a fictional light beam slicing through ice, but a concentrated energy pulse delivered through fiber optics. The advantage is precision. No hot water. No fluids. No risk of chemical contamination. Just controlled energy melting a narrow shaft downward. The problem is scale. A shaft deep enough to reach the underice world would require enormous power. Delivering that power in the Arctic, safely and reliably, is its own engineering nightmare. Still, the idea refuses to die. Every year, new versions emerge, more efficient than the ones before. Then there are the hybrid concepts. Systems that blend drilling, melting, autonomous navigation, and swarm robotics. Imagine dozens of small probes working together, each one mapping a tiny section of the underice labyrinth. Alone, they would fail. Together, they could cover enormous distances, relaying data between one another like a chain of glowing breadcrumbs. Some researchers imagine using the ice itself as part of the system. Letting natural melt channels guide autonomous vehicles. Letting pressure gradients carry instruments downward instead of fighting them. Working with the glacier rather than against it. These ideas sound ambitious, and they are. But ambition is exactly what the Arctic demands. We already know what doesn't work. We've proven that brute force alone won't open the door beneath the North Pole. The ice is too thick. The environment too unstable. The risks too great. So innovation becomes the only path forward. Not because it's convenient, but because it's necessary. And yet, even with all these technologies on the horizon, something unexpected becomes clear. The deeper you think about it, the more you realize that drilling, melting, and robotics are only part of the story. The barrier isn't just physical. It's conceptual. It forces us to ask what exploration actually means. Because reaching the hidden world beneath the Arctic won't just require new machines. It will require a new mindset, a way of exploring that respects isolation, a way of observing without destroying, a way of learning without taking. That's where the path leads next. There are places on Earth that feel untouched. The high Arctic is one of them. It is a kingdom of ice that stretches beyond the horizon, cold enough to silence entire landscapes, old enough to remember worlds that vanished long before ours began. But the true kingdom isn't on the surface. It's below. When you stand on the Arctic ice, you are standing on the roof of a hidden world. Kilometers beneath your feet, pressure reshapes ice into something dense and ancient. The glacier becomes a living structure, a layered history carved into frozen walls. Every winter adds another page. Every 1,000 years adds another chapter. And the kingdom grows downward, tightening its grip on everything below. Most people imagine the Arctic as a flat sheet of white. But this kingdom is anything but flat. The ice rises in ridges, collapses in fractures, and flows like slow rivers frozen in time. Its peaks stretch towards the sky. Its valleys sink deep enough to swallow mountains. Hidden beneath those valleys are basins carved over millions of years, large enough to hold entire lakes, wide enough to host networks of black water that never see the sun. In this frozen kingdom, warmth is the anomaly, a rare intrusion. But even the faintest warmth changes everything. Pressure increases with depth. As the glacier grows heavier, the lowest layers soften and deform. Ice begins to behave less like stone and more like a thick, heavy fluid. That slow flow reshapes the world beneath it, squeezing rock, grinding mountains, and trapping pockets of meltwater in the coldest darkness known on Earth. The pressure is so intense that it melts ice even when temperatures remain well below freezing. Water forms in thin films and hidden channels, threading its way through a labyrinth shaped by time and weight. That water sometimes collects, sometimes drains, sometimes becomes a lake sealed beneath kilometers of ice, isolated for longer than the age of human civilization. To call this a kingdom is not poetic exaggeration. It is layered. It is vast. It has deep history. It contains realms we cannot reach. And like any kingdom, it has borders that are difficult to cross. The ice is always watching, always moving, always resisting. Surface storms reshape the upper layers. Pressure shifts alter valleys below. Entire regions rise or fall by meters as the ice adjusts to forces we still cannot fully predict. And in this kingdom, nothing remains still. Not the ice, not the water, not even the ground beneath it. Under the weight of millions of winters, the land itself bends. The crust bows downward under the glacier's mass. Then, slowly, over thousands of years, it rises again when the ice retreats. This rising and sinking shakes the kingdom's foundations, redirecting water, shifting basins, and rewriting maps we thought were stable. The frozen kingdom is ancient, but not timeless. It feels alive. It moves. It breathes through pressure and flow. It hides things. It reveals almost nothing. And it stands between us and everything we want to learn. This is the kingdom we must cross to reach the world beneath. But crossing it comes with a cost. Because the deeper we go, the heavier the weight becomes. And that weight is not just physical. It's something else. Something that grows colder the further we descend. And that leads us into the next truth about the Arctic beneath the ice, one that explorers feel before they ever see it. a truth shaped not by temperature, but by time itself. The Arctic looks simple from above. A white sheet, a silent plain, a place where nothing seems to move. But that simplicity is a lie. Because every glacier you see, every ridge and every frozen valley is carrying the weight of time itself. Layers built from storms older than our civilizations. Snow that fell before any human language existed. Winters stacked upon winters, pressed into a record of the planet that stretches far beyond anything we can comprehend. Stand on a glacier, and you stand on history. Each layer holds a moment, a year, a century, locked away by cold, sealed by pressure, hidden from everything except the slow machinery of ice. As more snow falls, the weight increases. The air trapped between crystals is squeezed out. The ice becomes denser, harder, more unforgiving. Over thousands of years, those layers fuse into something closer to stone than frozen water. And with every new winter, the weight grows. That weight is more than mass. It is force. It is pressure reaching hundreds of atmospheres in the deepest places. It pushes down on the bedrock. It grinds mountains into dust. It crushes any cavity unlucky enough to fall beneath it. The ground doesn't resist. It yields. Earth's crust bends under the load, sinking hundreds of meters in some regions. When the ice retreats, the land slowly rises again, but the process takes centuries. That rising, called isostatic rebound, continues long after a glacier disappears, like the Earth remembering a burden long removed. Beneath the Arctic ice, that burden never left. The pressure at the base alters everything. Water behaves differently there, slipping between solid and liquid states depending on the slightest change in temperature. Ice softens under stress. It flows like a slow river, even when the surface remains still. The deeper the ice, the stranger the physics become. A few degrees of warmth created by friction can melt pockets of water. That melt spreads. It lubricates the glacier from below. It creates sliding, grinding, and reshaping that we can't see but can feel in the data. The glacier becomes a living machine, a system driven by weight and time. That is what makes exploration so difficult. Every probe we send down must endure pressures that bend metal. Every sensor must survive an environment where even a tiny miscalculation can crush it instantly. Ice doesn't care what we build. It doesn't notice when we try to force our way inside. The weight of a million winters is indifferent. It presses downward with the same patience it has always had. But the pressure doesn't only act downward. It acts outward too. Deep inside a glacier, ice crystals stretch and deform. They bend into new shapes under the load. They push against each other, rearranging themselves in a slow ballet of microscopic movement. Over time, this creates flows, currents, internal rivers of ice that move unseen. The weight above pushes the ice outward toward the sea. It turns the entire glacier into a massive conveyor belt, carrying ancient fragments of snow toward the coast where they eventually break off as icebergs. When something interrupts that flow, the glacier doesn't stop. It builds pressure. Pressure that will be released one way or another. Sometimes the release is slow. Sometimes it's catastrophic. Ice shelves collapse. Crevasses split open. Cavities burst and send meltwater surging beneath the ice in sudden floods known as Yerkelorps. These floods can carve new pathways in hours, rewriting the under-ice landscape faster than any human can track. All of this because of weight. Silent, constant, relentless weight. The longer a glacier exists, the more powerful this force becomes. The Arctic glaciers have existed a very long time. Some of the ice beneath Greenland is over 100,000 years old. Some layers formed during the last ice age, when massive sheets covered Europe and North America. Some fell as snow when woolly mammoths still roamed. When we study this ice, we're not just studying climate. We're studying time itself. Time you can touch. Time you can drill. Time that pushes back. And that brings us to the most important point. The deeper we go, the older the ice gets. The older it gets, the stronger it becomes. The stronger it becomes, the harder it tries to push us out. Beneath every glacier in the Arctic, the weight of 1,000,000 winters is waiting. Waiting to crush a drill shaft. Waiting to seal a borehole. Waiting to distort a sensor. Waiting to remind us that we are temporary and the ice is not. If we want to continue downward into the deeper mysteries, we have to respect that weight. We have to understand it. And we have to accept that it will never stop working against us. Because the ice isn't just heavy. It's alive with pressure. And pressure is the first guardian of the world beneath. There is a point beneath the Arctic where light disappears completely. Not dimmed, not filtered. Gone. Above it, the sun still rises and falls. Storms rage. Ice shifts. The world moves. But down here, none of that matters. This is a place where darkness is not just an absence. It is a presence. The deeper the ice becomes, the more it blocks every trace of the surface. Photons cannot travel through kilometers of frozen water. Not even the faintest glow survives the descent. What remains is a darkness so complete that even animals adapted to deep oceans would be blind here. This darkness changes everything. Sensors behave differently. Temperatures fluctuate in ways we still struggle to predict. Water flows without the influence of sunlight, without tides, without seasons. Every part of the environment becomes governed by pressure, chemistry, and time instead of light. For a robotic probe, this creates a world with no visual reference. No horizon. No shadows. No color. Only the faint patterns of sonar, the echo of movement, and the internal clock counting the seconds in the void. To us, darkness feels empty. But beneath the Arctic, darkness is full. It's filled with ancient water that has never touched the air. Sediments that hold records older than the human species. Chemical gradients that might feed microbial life. And it is filled with silence. A silence so complete you could almost believe the world has ended. But the darkness is not still. Rivers flow here. Hidden lakes expand and contract like slow, steady breaths. Channels open and collapse without warning. Pressure builds and releases in rhythms more ancient than any glacier on the surface. If life exists in this depth, it has adapted to a world without sight, warmth, or color. It would not recognize the sun. It would not recognize the concept of day. It would live in a constant night, shaped by chemistry, not by light. This is the kind of place that forces us to confront our limits. We build machines that see. We navigate with sensors and light. But beneath the Arctic ice, none of that works. We must rethink what exploration means. We must design tools that can function in a world shaped entirely by darkness. And that darkness is unforgiving. One mistake, one miscalculation, one failed sensor, and the mission is lost. Robots fail. Batteries die. Systems freeze. Navigation drifts without visual cues. And once the darkness consumes a machine, it rarely gives it back. Yet this is also why we keep trying. The darkness beneath the Arctic holds things we cannot find anywhere else on Earth. It holds secrets from the earliest days of the planet. It holds evidence of climates long vanished. It might even hold forms of life, adapted to a world with no sun. To reach them, we must enter the dark, not with fear, but with understanding. Because down here, light is not a guide. Patience is. Pressure is. Time is. And the darkness, vast and absolute, is only the beginning. Beneath the Arctic glaciers, beneath the pressure, beneath the silence, there may be something far larger than rivers or lakes. Something deeper. Something closer to an ocean than anything we've ever imagined beneath a sheet of ice. And the truth is simple. We don't fully know what's down there. Radar hints at it. Gravity measurements suggest it. Subtle changes in the ice reveal patterns we can't explain. Signs of enormous reservoirs. Not puddles, not channels, but vast, interconnected bodies of water sealed away in total darkness. These hidden oceans don't look like the oceans we know. They aren't open spaces with waves or tides. They are networks of deep basins carved by ancient ice. Basins linked by narrow passages where water flows slowly, quietly, under crushing pressure. Imagine a world where water never sees the sky, where no breeze ripples the surface, where no sunlight has ever reached, where time moves differently because nothing disturbs it. That's the world beneath the Arctic's frozen shield. Some of these subglacial basins may be the size of small seas. And they are not static. They rise. They fall. They drain. They refill. All without ever touching air. Scientists have seen this behavior in Antarctica, where entire lakes disappear in a matter of days as water escapes through hidden channels. Then months later, the lake fills again as if nothing happened. The Arctic almost certainly hides the same kind of systems. We just can't see them directly. The shapes of these hidden oceans are dictated by geology. Deep troughs carved by ancient glaciers. Rifts created by tectonic forces. Depressions shaped by the weight of the ice itself. Over time, meltwater collects in these spaces. Geothermal heat warms them slightly from below. Pressure lowers the melting point of ice above. And slowly, quietly, oceans take shape. These waters are cut off from the world. Nothing from the surface reaches them. No dust. No oxygen. No sunlight. Only the chemistry of rock. Only the pressure of ice. Only the steady heat rising from Earth's crust. If life exists in the Arctic's hidden oceans, it would not resemble anything from the surface. It would have adapted to darkness, extreme pressure, and scarcity. This isn't speculation. We've already found life in Antarctica's subglacial lakes. Microbes that metabolize iron, sulfur, and hydrogen. Organisms that survive in water colder than the freezing point of seawater. Microbes sealed away for 500,000 years. If such life thrives beneath Antarctica, there is no reason the Arctic would be any different. In fact, the Arctic might be even more dynamic. Its hidden oceans may connect to the sea in ways we don't yet understand. Warm currents could seep beneath the ice and feed these reservoirs. Minerals from the bedrock could create chemical gradients that fuel microbial metabolism. But until we reach these places, everything remains an unfinished puzzle. Even our best technology struggles here. Radar becomes unreliable at great depths. Acoustic signals scatter. Drilling risks contamination. Robots cannot navigate channels we've never mapped. This is why, even today, the Arctic's hidden oceans remain more mysterious than the deep sea. They are close. They are beneath our feet. Yet they might as well be on another planet. Reaching them is more than a scientific goal. It's a test of whether we can explore without destroying. A test of whether we can enter an untouched world without rewriting it simply by opening it. Because once we break through the ice, the ecosystem below, if it exists, changes forever. The ocean beneath the Arctic glaciers has waited for millions of years. It will not open itself easily. And that may be the clearest sign of all. Some worlds resist us because they're dangerous. Others resist us because they're fragile. The hidden oceans of the Arctic might be both. For decades, we've tried to reach the hidden world beneath the Arctic ice, and every failure has forced us to rethink our approach. Not because our engineers lack skill, but because the ice itself behaves like an opponent. It shifts, squeezes, bends, and crushes anything that enters it. So we adapt. We redesign. We rebuild. And slowly, machine by machine, we get closer. The first attempts were simple: heavy drills, steel cables, fuel lines that froze in minutes. Those tools were built for the ground beneath our feet, not the moving crust of a frozen ocean. Next came thermal drills. Long cylinders heated from within, designed to melt their way downward. They worked for a while, but the ice closed up behind them, sealing the shafts as fast as they opened them. Some drills were lost forever, swallowed by the very medium they tried to cut through. Then came the generation of clean drills, designed with one goal in mind. Do not contaminate anything. Every bolt sterilized. Every drop of fluid purified. Every cable flushed with UV light. Because even a single microbe from the surface could ruin the fragile ecosystems we're trying to study. These drills succeeded in Antarctica. But the Arctic is a different beast entirely. The ice here floats. It drifts. It cracks. A station can move kilometers in days, pulling machinery with it. A perfect borehole can be destroyed overnight by pressure ridges rising from the deep. So engineers changed direction again. Robotic crawlers were built to cling to ice surfaces, crawling like metal insects across shifting terrain. Some were small enough to fit in a backpack. Others were the size of compact cars, designed to anchor themselves with ice screws and survive storms that would tear tents to shreds. Then came the AUVs, autonomous underwater vehicles, machines built for the dark water beneath floating ice shelves. Torpedo-shaped bodies equipped with sonar, navigation sensors, and batteries built for extreme cold. They could map underwater terrain, track currents, and even record the sounds of cracking ice. But even these machines had their limits. Communication is almost impossible. Radio waves die in the ice. GPS signals vanish the moment you go under. Acoustic signals warp and scatter. Once an AUV goes beneath the glacier, it becomes a ghost. Alone. Silent. Unrecoverable if something goes wrong. And beneath the glaciers, things go wrong constantly. Some vehicles returned with their hulls warped by pressure. Others vanished entirely, never detected again. One machine sent from Greenland returned with grooves scraped deeply into its side, likely from ice grinding against it. A reminder that even small contact with a shifting ice wall can be lethal to metal. Still, the work continues. Newer machines carry stronger hulls made of titanium alloys. Their sensors are protected with shock absorbers. Their batteries are built for cold far below freezing. They travel farther and last longer than anything before them. Some designs are visionary. Cryobots heated by small nuclear sources. Hybrid robots that melt through ice, then swim once they hit water. Swarms of tiny microbots that coordinate together to map out labyrinths no single probe could survive. Each idea pushes the boundary. Each prototype reveals new rules. Each failure teaches us more about the enemy. Because the truth is simple. If we ever want to reach the world beneath the Arctic glaciers, we must build machines that don't just survive the ice. They must understand it, predict it, flow with it, respect it. The machines we build reflect us. Stubborn, curious, driven to go where we've never been. And as they grow more advanced, they push us toward the edge of something bigger. Something that forces us to face the next question. Not how to get through the ice, but what waits for us once we do. Ice looks simple from the surface. A frozen sheet, a white plain, a quiet world where nothing moves. But beneath that simplicity lies a set of rules that govern everything under the Arctic. Rules that don't bend. Rules that don't care who tries to challenge them. And every attempt to reach the hidden world below crashes against those rules. The physics of ice is the real gatekeeper of the Arctic. It decides how far our drills can descend. It decides where water flows. It decides which machines survive and which are crushed. To understand why we still haven't reached the world beneath the North Pole, we have to understand how ice behaves, not in a glass, not on a winter lake, but at the scale of continents. Ice under pressure is not solid in the way rock is solid. It creeps. It bends. It flows. Push down on it with enough force, and it begins to deform. Under the weight of kilometers of ice pressing on itself, the entire mass becomes a slow river. A river that moves in centuries, not seconds, but one that moves all the same. This movement matters, because nothing inside a moving glacier stays where you expect it to. Layers tilt. Fractures open. Channels shift direction. Anything placed inside, it is carried away like driftwood caught in a tide. Then there is temperature. Ice is cold, but it is never evenly cold. Near the surface, temperatures plunge far below freezing. Deeper down, pressure lowers the melting point. Heat from the Earth's interior creeps upward. Friction from the glacier's movement generates warmth. These forces combine to create a strange zone at the glacier's base. A place where ice is solid one moment, slushy the next, and liquid water appears in pockets and channels carved through the bed. It is this liquid water that keeps the labyrinth alive. It opens pathways. It floods chambers. It refreezes into walls thicker than concrete. For explorers, that shifting balance between solid ice and flowing water creates a nightmare. Too much heat, and the ice softens, squeezing shut any borehole we drill. Too little, and the drill freezes in place, trapped forever. Pressure adds another layer of danger. Every meter deeper increases the weight above. At a few hundred meters, equipment must already withstand more pressure than most submarines face. At 1,000 meters, steel begins to deform. At 2,000, only specialized alloys and reinforced composites survive. At 3,000, few machines humanity has ever built can endure it. Then the water beneath the ice adds its own complications. Subglacial lakes are often pressurized far beyond atmospheric levels. Break into one too quickly, and the lake water rushes upward with explosive force. Enter too slowly, and the pressure outside may crush the probe. Even the shape of ice crystals matters. Over centuries, the crystals stretch and realign under stress. They form layers that slide over each other, layers that force instruments sideways or twist cables until they snap. Every rule of physics that governs ice becomes a barrier. Every barrier becomes a risk. Every risk becomes another reason we still haven't reached the world beneath the Arctic's glaciers. But these rules are not obstacles by accident. They're the natural laws of a frozen system, sculpted by pressure, gravity, and time. A system older than our species. A system that doesn't change for us or for anyone. If we want to explore what lies beneath, we must work with these laws, not against them. Because ice will always behave like ice. And until we understand the rules fully, we will always be outsiders standing on the surface, staring down into a world we cannot yet enter. Even in the deepest cold, nothing under the Arctic stays still. The ice may look frozen in place, but beneath the surface, the entire world is constantly shifting. The glaciers move first. They creep forward under their own weight. Not fast, not dramatic, but steady, always steady. A few centimeters in a week, a few meters in a year. Over centuries, that slow crawl becomes a rearranging of the entire landscape. Every movement leaves a mark. Crevasses open, old ones close. Channels that once carried meltwater are swallowed by the changing ice. Hidden basins rise or collapse, sealed off from the world above. This constant motion makes the land beneath the ice one of the most unstable places on Earth. Not unstable in the sense of danger, but unstable in the sense of change. The Arctic is never the same place twice. And that movement is not gentle. It twists, it grinds, it reshapes everything below. Under the glacier, the ice presses against the bedrock, carving valleys, dragging boulders, and crushing sediment into fine powder. Every scrape creates new pathways for meltwater. Every shift closes another. The water itself moves too. It flows through channels that open like veins, sometimes roaring with pressure, sometimes slowing to a trickle. A lake might stay in one place for centuries, then drain in a single night. A channel might stay open for generations, then freeze shut before anyone can measure it. And all of this happens in the dark. No human sees it. We only see the aftermath. A bulge in the ice, a sudden shift in velocity, a signal from radar that doesn't match the last one. This is the heart of the challenge. The Arctic beneath the glaciers is not a structure. It is a process. A system defined by motion, not by form. And while the surface tells one story, the depths tell another. At the surface, the ice drifts with wind and sea. At the base, the glacier slides over rock, warmed by the earth below. And in the middle, the ice deforms slowly, pushed and pulled by the forces above and below. Every layer moves differently. Every layer stretches or compresses at its own pace. Sensors that descend into this shifting body of ice don't just enter darkness. They enter a moving maze. Even the most advanced models struggle to predict what happens next. The forces are too many. The changes too subtle, too constant. A tiny increase in pressure can collapse a cavity. A slight change in temperature can melt a channel open. The Arctic beneath the ice refuses to sit still long enough for us to understand it. And that complexity is not an obstacle, it's a signature. It tells us this environment is alive in its own slow, powerful way. A world shaped not by light or seasons, but by pressure, gravity, and time. We are used to thinking of motion as something we can see. But here, motion is something you feel only in the results. A glacier that ends the year in a different place. A lake that no longer exists. a landscape rewritten without ever being seen. This is why we struggle to explore it. It isn't hostile because it wants to be. It's hostile because it moves. Because every path we try to follow is shifting beneath our tools. And yet, this motion is part of what makes the Arctic so compelling. A place that refuses to remain what it was yesterday. A place that demands patience, humility, and persistence. Because the deeper we go into this moving world, the more we realize something simple and unavoidable. To explore the Arctic beneath the ice, we don't just need better machines. We need to understand the motion itself. And that journey leads straight into the next challenge, where motion meets climate, where the world below answers to the world above. The Arctic does not change quietly. It changes with force, with heat that shouldn't be there, with storms that didn't exist a century ago, with ice that melts from above, below, and from within. And every one of those changes reaches deep under the glaciers, into the places we're trying so hard to explore. People talk about climate change as if it's only happening on the surface, as if rising temperatures and shrinking ice sheets are the whole story. But beneath the glaciers, the consequences run far deeper. The labyrinth under the ice, the one scientists have been trying to reach for decades, is being reshaped by a warming world in ways that make exploration harder, riskier, and more unpredictable than ever. Warm air melts the upper layers. Warm oceans carve at the base. Meltwater finds cracks that never existed before, rushing downward in violent pulses. Each drop of warmth becomes a change in pressure. Each new channel becomes a shift in flow. And each shift rewrites the map we thought we understood. Some parts of the Arctic see more snowfall now. Heavy, wet snow that adds weight and increases pressure on the ground below. Other regions see far less, thinning the ice and allowing summer warmth to penetrate deeper. These differences matter. They decide how the ice moves, whether it creeps, whether it fractures, or whether it suddenly surges forward in ways that destroy instruments and bury years of planning. Then there's the ocean, the quiet accomplice. Warm currents now push farther beneath floating ice shelves, melting them from below and destabilizing everything upstream. When a glacier loses its support at the front, it accelerates, it stretches, it cracks. The whole system speeds up like a machine suddenly unbalanced. And that instability travels inward, toward the subglacial lakes, toward the hidden rivers, toward the ancient pockets of water that we're desperate to reach before they change forever. Permafrost responds too. Ground that stayed frozen for tens of thousands of years is thawing. When it softens, the landscape underneath the ice shifts. Sediments collapse. Channels redirect. Drainage patterns flip. The foundation itself begins to move. All of these forces combine into something the Arctic has never faced at this speed. Not in the last 1,000 years. Not in the last 10,000. The system is still governed by physics. But the inputs are different now. The rules are the same. But the game is changing faster than the ice can adjust. For explorers, this means one thing. Nothing stays still long enough to plan around. Not the ice. Not the water. Not the landscape. By the time we gather data, the environment has already moved on. The hidden world beneath the Arctic is not just inaccessible. It is unstable. And every year, it becomes a little more so. But this instability isn't only a threat. It's also a warning. A signal that whatever lies beneath the glaciers may not remain untouched for much longer. If we want answers, we may have to find them soon, before the Arctic rewrites itself again. Deep beneath the Arctic glaciers, far from sunlight, wind, or anything familiar, there may be places where life endures. Not life as we know it from forests or coral reefs. Something far more fragile, far more patient, far more strange. If life exists beneath the ice, it has adapted to a world defined by absence. No light, no warmth, no oxygen from the atmosphere, no seasons, no day or night, only pressure, darkness, and time. Most people imagine life as something that needs sunlight. Plants turn light into energy. Animals eat the plants or eat animals that eat plants. Entire food webs depend on the sun. But in the 1970s, that idea began to collapse. Scientists found deep ocean vents pouring out superheated water rich in minerals. Around them lived ecosystems that had never seen sunlight. Giant tube worms, blind crabs, clams the size of helmets, and at the heart of it all, microbes using chemicals instead of sunlight. They used hydrogen sulfide and iron to fuel themselves. This changed everything. It proved life can grow in darkness if there is water, energy, and time. Beneath the Arctic glaciers, those same conditions exist. The water under the ice is pitch black, oxygen poor, and under crushing pressure. But chemical gradients exist there. Iron from rock, sulfate, hydrogen, mineral particles carved loose by the grinding ice, all potential energy sources for microbes. We already know this is possible because we've seen it in Antarctica. Lake Vostok, buried beneath 4 kilometers of ice, contains microbial life sealed away for millions of years. Other lakes beneath Antarctica show the same thing. Microbes metabolizing iron and sulfur. Microbes using hydrogen created by rock-water reactions. Microbes devouring ancient organic matter trapped long before humans existed. If such ecosystems exist beneath the Arctic, they would be sparse. A few thousand cells per milliliter at most, but they would be alive, and their existence would rewrite our understanding of biology. They might represent ancient lineages that diverged from surface life hundreds of thousands of years ago. They might hold metabolic strategies unlike anything we've seen. They might show us how life survives isolation, scarcity, and pressure. And they would push the boundaries of habitability on Earth. This has implications far beyond the Arctic. Europa, Enceladus, Titan, Ganymede, worlds where oceans hide beneath ice, worlds with chemical energy but no sunlight, worlds with conditions that mirror our own subglacial lakes. If life endures beneath Earth's ice sheets, then it might endure beneath the ice of distant moons. Microbes surviving on minerals and chemistry instead of light. Studying the Arctic's hidden biospheres could become a preview of alien biology. But reaching these potential ecosystems is anything but simple. Drilling risks contamination. A single surface microbe is enough to overwhelm a native environment that has never experienced competition. A change in temperature from a drill could shift the chemistry. A tiny leak of drilling fluid could erase an entire ecosystem. We have to approach with extreme caution. Even when samples are recovered, distinguishing true native life from contamination is extremely difficult. Instruments must be sterilized completely. Every seal must hold. Every sample must remain untouched until analyzed. And even then, uncertainty remains. It's also possible the life down there isn't thriving. It might be dormant, waiting, metabolizing so slowly that generations pass in centuries, dividing once in a human lifetime, barely clinging on. If so, studying them could reveal how life persists when conditions are unforgiving and energy is scarce. It could show us that survival is not always dramatic. Sometimes it's quiet, patient, almost ghost-like. Life beneath the Arctic ice, if it exists, would not be abundant. It would not be spectacular, but it would be profound. It would expand the definition of where life can survive. It would show us that biology isn't fragile. It adapts, even in silence. And it would remind us that the Earth still hides entire worlds we have yet to understand. Far beneath the Arctic ice, in the coldest and most isolated places on Earth, something unexpected happens. The deeper we look, the more the environment stops feeling familiar, and the more it begins to resemble worlds we have never walked on. The frozen chambers under our own glaciers are not just geological structures. They are mirrors, reflecting places far beyond this planet. This is where the Arctic becomes more than a region. It becomes a bridge. Beneath the North Pole, conditions form that we once believed were rare, perhaps even impossible. Absolute darkness, crushing pressure, water sealed away for thousands, maybe millions of years. Chemical energy feeding ecosystems without sunlight. It sounds alien because, in many ways, it is. And yet these conditions are not unique to Earth. Across the solar system, there are worlds defined by the same ingredients. Europa, one of Jupiter's moons, carries a shell of ice tens of kilometers thick, covering a hidden ocean larger than all the oceans on Earth combined. That ocean never sees sunlight. It is heated from below by tidal forces and perhaps volcanic vents. If life exists there, it would live the way life might live beneath our glaciers, feeding off minerals, chemistry, and the trace amounts of energy that seep from rock into water. Enceladus, a small moon of Saturn, tells a similar story. Its icy surface hides a deep ocean, and along its south pole, geysers blast water into space. Analysis of those plumes shows organic molecules, salts, and tiny grains formed by interactions between rock and warm water. To scientists, that is the signature of a hydrothermal system, the kind that sustains entire ecosystems at the bottom of Earth's oceans and potentially beneath Arctic glaciers. Even farther out, moons like Ganymede, Callisto, Titan, and possibly Pluto also show signs of hidden oceans. A pattern emerges. If you want liquid water in a cold universe, you hide it beneath ice. Suddenly, Earth's polar regions do not feel distant or exotic. They feel relevant. They feel like practice. When we study the Arctic's subglacial lakes, we are not just exploring Earth. We are rehearsing for places humans may reach generations from now. The problems we face here, penetrating thick ice, avoiding contamination, navigating dark water under impossible pressure, are the same challenges any mission to Europa or Enceladus will face. The Arctic becomes a test bed, a proving ground, a chance to fail safely on Earth before attempting the same thing hundreds of millions of kilometers away. Every drill we refine here, every probe we recover, every microbial sample we protect from contamination lays the groundwork for reaching those distant oceans. And every failure teaches us what not to do when the stakes are infinitely higher. There is a deeper question beneath all this. If life can survive under Earth's ice, in the dark, with only chemical energy to sustain it, then life may not be rare. It may be common. It may appear wherever ice and water coexist. Suddenly, the universe feels less empty, less silent. The Arctic holds up a mirror, not just to other worlds, but to ourselves. It shows us what we value, what we fear, and what we hope to discover. It reminds us that Earth is not isolated, but part of a larger family of icy, water-rich worlds scattered across space. And as we stare into that mirror, one truth becomes clear. To understand what might live light years away, we first need to understand what lives beneath our own feet, sealed in darkness, waiting for us to finally reach it. There is a point in every exploration where the path turns inward, where the question stops being what is out there and becomes how far should we go. The world beneath the Arctic glaciers forces that question onto us with unusual clarity. We have the technology to reach many places. We can map deserts from orbit. We can dive to the bottom of the Pacific Trench. We can land machines on Mars. But beneath kilometers of ancient ice, something is different. The resistance feels deeper than physics, stronger than engineering. It feels intentional. Not because the Arctic is alive, but because it behaves like a place that deserves to be left partly unknown. Beneath those glaciers, pressure crushes rock into powder. Darkness erases time. Water flows in silence. Whatever exists in those caverns has lived, evolved, or simply endured without sunlight or disturbance for hundreds of thousands of years. To break into that world is not a casual act. It is intrusion. One slip of a drill could erase an ecosystem. One trace of modern bacteria could overwhelm life that has never faced a competitor. One mistake could collapse a chamber sealed since the Ice Age. We can study it. We can try to reach it. But we cannot pretend that our presence leaves nothing behind. As explorers, this is the line we struggle with. The desire to know pulls us forward. The responsibility to protect holds us back. And beneath the Arctic glaciers, those two forces crash together harder than anywhere else on Earth. The mystery is not there to frustrate us. It is there to humble us. Because some places are not meant to be conquered. Some places are meant to be approached with caution, patience, and a willingness to let part of the story remain untold. And strangely, that is what makes them powerful. Mystery is not ignorance. Mystery is the reminder that we are not the center of everything, that the world is older than our tools, that nature still keeps secrets, not because it must, but because the universe is bigger than our reach. The hidden world beneath the North Pole will not stay hidden forever. One day, our machines may melt through every barrier. One day, we may explore those dark rivers and untouched lakes with gentle precision. One day, we may hold answers we can only imagine now. But even when that day comes, something essential will remain beyond us. The Arctic's silence, its scale, its indifference to our ambition. Those are not things we can drill into. They are truths we can only learn by respecting the boundaries in front of us. And perhaps that is the real lesson. Not that the Arctic resists us, but that it teaches us how to explore without destroying. How to seek knowledge without taking everything. How to wonder without needing to possess. In the end, the greatest mysteries are not the ones hidden beneath ice or trapped in darkness. They are the ones that shape us as we try to reach them. And so the Arctic keeps its secrets for now, not as a barrier, but as an invitation to proceed with care. A reminder that some questions are most powerful when they remain partly unanswered, and that sometimes the mystery must remain.